The theory of 1 plus 1 equals 1 of something else revisited. Hi, I'm here to give you a little lesson in a different perspective. Now, I'm not saying that 1 plus 1 doesn't equal 2. I'm saying that 1 plus 1 doesn't always equal 2. And using your mind and critical thinking, you might come to a different, say, conclusion to whether 1 plus 1 equals 2 or it doesn't. I'm just saying that 1 plus 1 equals 1 of something else. And your own critical thinking ought to determine what that is. So let's just start off with 1 plus 1. I draw a 1, and then a plus sign, and then another 1, and then an equal sign. Now my question to you is, how many 1s are there? Now you might say that there's a 1 there, and a 1 there. But isn't there also possibly a 1 in that direction, and a 1 in that direction, and a 1 in that direction, and a 1 in that direction? We see that this could have 1, 2, 1, 2, 3, 4, or 1, 2, 3. So this could be broken down into 2, 3, or 4 1s. Or it could also be broken down into an infinite set of 1s, but we'll leave that for another time. In any case, if we were to look at this from a hieroglyphic standpoint, I would say that you had one stick, and you had another stick, and you stacked the two sticks on top of each other, right? And then if we were to say, well, how many sticks do we have? If we were to order them and line them up, we would write down 2, right? Except there's only one problem. They're 2 straight lines, right? 2 straight vectors. There's a curve and a line there. That's obviously not 2 lines. Wouldn't it have been better, instead of using this 2 symbol here, to have something look like that, or have something that looked like that, or something that looked like that? I mean, that would be a closer representation to 1 plus 1, wouldn't it? Well, we have to go back in time, so to speak, and we have to look at the number that precedes 1. And the number that precedes 1 is 0, right? So you go from 0 to 1, okay? And what is 0? 0, for a better word, for lack of a better word, would be a circle. So you have a circle and a vector, right? A 0 and a 1, the first 2 numbers. So if I was to break this circle up into smaller pieces, I could say there's 2 half circles there, right? And I could break this 1 up into smaller vectors, into individual vectors, so to speak. And then we find that the 2 is a representation of a combination of half circles and, 1 half circle and a vector. So we get 2, right? But you didn't originally start off with that, did we? We had a vector and a vector. And somehow that vector turned into some sort of curve. I'll simplify it and just say it's a half circle. In any case, we also would, if you're going to get all technical about it, we could also look at the digital 2, and that would look like that. And it's a combination of vectors, which is a closer representation, but we have 4 vectors and not a vector in a half circle or a curve. So there's a digital 2. Right? So why am I explaining this in this way? Well, the idea is that we have to approach mathematics from a, shall we say, hieroglyphic or a symbolic perspective. Instead of just ignorantly saying that it equals 2, why don't we look at what's actually happening? What is actually occurring in these symbols? That we're taking 2 vectors and we're stacking them up on top of each other, 90 degrees separated. And then we're going to split those 2 vectors up, and we're going to look at those 2 vectors, and then we say, well, those 2 vectors represent the symbol, which is a vector and a curve, or a vector and a half circle. Now, going back to the 0 and 1, we could also say that the 0 right here is representative of, if we were to draw a center point, center of the circle, and we were to draw a radius out, right? That's a vector, just like the 1. And we rotate that vector going around in any direction. That creates our circle. So anything can be broken down into a vector or a radial vector. Yes, makes sense. So when I say 1 plus 1 doesn't always equal 2, it means that if I add two vectors together, I'm going to get another vector, and it might be, for example, something that looks like that, or something that looks like that, or something that looks like that, or all kinds of different combinations. Why did we choose that? Why is it like that? Maybe there's hidden meaning in this, and nobody's ever tried to think about it in that way, and it's just for the ignorant masses to just say, oh, 1 plus 1 equals this curve and a vector, and nobody questions it because everybody accepts it. Well, I don't accept everything like that, and I'm just saying that if you want to use some critical thought in your mind, this is one way of approaching it. Okay, let's look at another case example here, and if I was to just draw some sort of random squiggle, as we should say. Now, let's say that this squiggle is in three-dimensional space. Now, there's two ways of measuring it. Actually, there's an infinite amount of ways of measuring it, but I'm just going to show you one. Okay? I'll show you one. Show you several different. So I could just pick a point in space here. And remember, this is 3 dimensions. And if I was to measure this, I could draw splines to this. And that's one way of measuring this out. And I could draw another point here, and I could measure this part out using this method. And we see that there's more than one way to recreate this curve, one way to recreate this squiggle in time and space, that there's many functions to it. Now, this is all was part of some work I was doing in writing unbreakable encryption codes and unbreakable encryption formulas. And I came across this idea and I said, wow, I could create these mathematical formulas and using both 3-dimensional and 4-dimensional informational matrices, and there's no beginning and no end to where it starts and where it ends of where this encryption algorithm goes. And if you don't have the key, which is the formulas, not just one but several, if you don't have the key to it, it's impossible to break, because you don't know where it starts, you don't know where it ends, and you don't know where the formula or how many formulas, and you don't know whether the data in there is actually good data or shit data, and you don't know anything. So this is one of these interesting things. So this is one way of measurement. And we notice that we're using what I would call radial vectors because they radiate out from this point. Okay? So that was one way of measuring this squiggle or curve or whatever you want to call it. So let's draw something equivalent to that. So it's supposed to be the same one, even though it's not to scale. So the next way of measuring this was we have a starting point here, and then we're going to incrementally measure each little change of, say, the point, and we would literally just trace this point. And so that was another way of creating a formula for where this squiggle mark lies in time and space. So they're just derivatives. They're just incremental linear derivatives or vector derivatives. And all you're doing is building this squiggling line up with a bunch of ones. So that's the theory of 1 plus 1, is that anything can be broken down into ones, or in this case, radial vectors or radial vectors, ones and zeros, right? So we could look at this as a function of some sort of circular pattern in both time and space, that we can write any formula for any perspective. When I mean perspective, I mean point that radiates towards that shape or object or whatever it is. And then we could write formulas for that. Okay, well, how does this relate to, say, practical ideas. Well, if we look at uh, what I call artificial intelligence, and I think that artificial intelligence, I should say, I believe that artificial intelligence is a very simple concept. And we look at this. What's it look like? It looks like two vectors. And here, if we draw two arrows, we would say these two vectors converge to a point, P, right? And if these vectors started here and radiated out, we would say these two vectors diverged from point P, right? So basically, we break things down into convergence and divergence. And then there's this, shall we say, a neutral state, which is running parallel. So that the vectors never, they never cross each other. They're always parallel to each other. And this represents basically no change in anything. Now, we don't really find this in nature. Things are constantly changing with respect to time. So, and, this idea that something or two ideas or two objects always stay relatively in the same position to each other, I don't particularly believe exists in nature, because things are moving and changing, and there's all kinds of vectors that we don't see, like magnetic flux and light, sound, vibrations, all these things. And so the vectors towards any, say, 2 points, say P1 and P2, so point 1 and point 2, that these points are never vectorally parallel to each other, that they're always having convergence and divergence from these 2 points in any specific domain. And what I mean by domain is a dimension. And we don't know what that dimension specifically is. We could say vibrational frequency, light, the measurement of photons, how fluid something is, viscous, things like that. I mean, there's all these different dimensions, and we can just keep on adding dimensions to these points P in both x, y, z time space with a factor of t time added as our fourth dimension. So x, y, z, t, and then say if we were to add magnetism in there and magnetic flux, we could call it x, y, z, and then m and t, or depending on how you want to arrange it, that's up to you. I'm not gonna get all, I'm not gonna get all particular about it. Okay, so how does this relate into, say, more practical work? Well, I've had the opportunity to live in Norway, and in the Norwegian language, their letters go from A to O, and in this it's just like A, B, C, D, and then all the way, and then you have and you have and you have O. And specifically, these two letters right here are very important in my interpretation of mathematics. And as you can see, this is basically, used in mathematics for angles, and different people use it for different variables. But the A with the O on top is one of the most fascinating characters to me, because let's move on to another sheet here. The A with the O on top, right there, and it is directly on top. Sometimes I write it without it being on top, but the O is on top of this A, and it's the last letter. If you were to look at this, and we were to look at the letter A that begins, it's basically like telling you that if we started with the letter A, and then we were to write B and C, and we would circle all the way back, right? And that tells us to symbolically circle around each one of these letters. So I would say that it begins at A, so this is where the alphabet starts, and it ends at O, and that basically is just telling you to repeat in a circle, and that O represents every letter between A and this letter A with the O on top, pronounced O. Okay, so B, C, D, and E, F, G, all everything in there is in this one letter. Okay, well, why is that important? Well, when you write formulas, and specifically in vector calculus and radial vector calculus, we use the integral like this. Here we have an indefinite integral, as we don't have any, starting point and ending point, so just an indefinite integral. And if we write this, well, this could be representative of a bunch of things, like it could have gravity in there, and it could have t as in time, and we could have, you name it, it's radiuses, and you could use the lowercase, uppercase, it represents it all, right? Because if you look at any character in the Western alphabet, it's a combination of vectors and half circles. You can draw any letter in both English and Norwegian and just about anything with vectors and half circles. Technically, if you keep on reducing a vector down to its smallest size, it becomes a pixel. When you reduce the scale down, anything could be reduced down into a vector. So the tiniest little incremental vector. So anything can be broken down into vectors and radial vectors, and that's why I like to use this letter, is because it represents all the vectors. It shows you the circle, it tells you what to do, and this little vector in here tells you the measurement in between vector. So if this was vector 1 right here and this was vector 2, we measure between those, and we're talking about radial vectors, and maybe it's a point. It represents a lot in that symbol. I mean, there's a lot going on in there. And, I see it from a hieroglyphical, symbolic standpoint. And, people here in Norway don't, they probably don't see it the same way. And I understand. And I'm not saying that you have to see it this way. I'm just saying it's there. But if we go back to convergence, and we said that things converge to a point, right? Or they radiate out to a point, or radiate out from a point, I should say, we notice that looks familiar, doesn't it? So we get these same ideas, these same concepts are built in here. That you have both convergence and divergence within that character as well. So like I said, a lot going on in that character. And that character this could be a representation of gravity. It could be a representation of time. It could be a radial representation that, for example, in encryption, if you were writing one of these encryption programs, what I call unbreakable encryption codes, you could have the radius changing in time and, fluctuating around, having fluctuations, usually in, different sine, cosine type ideas in there in the formula. And literally, this is representative of this. This is the convergence, divergence from point, and then you add in all these other variables. So that is why this character is so important. Okay. Well, then we get down to, okay, well, where is this useful in, what we call, more practical situations? Well, if I was to talk about solar systems, for example, and we were to look at the sun as in the center of our solar system, and you have different planets here, and they have this elliptical orbits, which is somewhat like a circular orbit, but we could say that those are radiuses that are changing, right? Notice how the sun and the radius in the orbit, the orbital path using vectors, represents that letter right there. And say another, if you were to have another elliptical orbit here, and this was changing position that we see, and then we can measure different changes, and voila, why that letter's so important. Why that letter tells you symbolically, hieroglyphically, what to do, where to go, how to break things down, how to look at things. So, and this is where, I talk about vector calculus, and, no matter how many vectors or radial vectors you add into your, so we call it your vector, you're just your single vector, it'll always be one vector with an infinite amount of dimensions to that vector. So this is, might be somewhat complex for some people. I don't think it's that difficult because it's all based on this idea of adding 1 to itself. And that 1 plus 1 equals 1 of something else. Like these vectors right here symbolically mean something different, and they have more than one meaning to it. This letter in this alphabet has more than one meaning, and it tells you a lot. It's telling you a whole heck of a lot. And if you don't want to believe it, that's fine. It's not like I'm in some religious cult and I'm expecting everybody to bow down and oh, this is the greatest. No, you believe what you want, man. I'm talking about critical thinking, man. I'm talking about using your brain and looking at things in a different perspective, not just accepting what you've been told, not just accepting that 1 plus 1 equals 2, but actually looking at what that 2 is, what it represents, what are these symbols, why are they there, and what are they telling you? And if you could break it down and build it back up and keep breaking it down and building it back up, you might see some patterns in there, and you might see some patterns in life, and you might see some patterns in people and the cosmos, and anything from chemistry to mechanics to whatever. It's all can be broken down into both linear vectors, which is the line vector, and radial vectors. And I'm sure that there's more other ways to doing this, but personally, I don't think that it really matters. I mean, literally, you can break things down into circles, half circles, and vectors, linear vectors, zeros and ones. And that's the way the computer is built. The modern day, binary computer is built on this. And even with the advent of they want to do quantum computing, even if you build the quantum computer, what the quantum computer can do can still be done, maybe not at the same speed or whatever, but it could still be broken down into these same concepts of breaking it down into radial vectors and linear vectors. So, maybe you're gaining some sort of speed advantage or, something like that. But in all practicality, the modern day binary computer is the alpha and the omega. And if you look at this character from going from A to O here, this is also the alpha and the omega. Notice A for alpha and O, just like this, and omega. And what's even more interesting was when in English, in both English and Norwegian, like when somebody says something and it causes you to think, what do you say in English? You say O, like O-H, O. Oh, well, guess what? In Norwegian, they say exactly the same thing. Like if somebody says something and it causes you to think, you say, oh, that letter right there. Oh. Because why? It represents some sort of movement in time and space. It represents a thought. It represents calculations going on. And it's much more than like language and numbers. It's much more than what people think. And that's why I constantly ask this question is, what's in a name? What's in a name? And for example, any letter in the alphabet can be broken down into a half circle and a vector. And your life is those half circles and vectors. And what you do with your life is you filling in those pathways. And that represents who you are. And you can be broken down into small little parts and built back up again, broken down into smaller parts and built back up again, over and over and over again, until somebody breaks you down and builds you up in the vision that they have. And that's the way it works. And maybe, they say you get red pilled and, blue pilled. I'm going to go with the transparent pill. This is the transparent pill. It's just, you can take it or leave it, see through it, don't believe it. Stick to 1 plus 1 equals 2. The commies are coming. They're telling me I have to believe it's 2. I believe what you want. I don't know. It's, it's up to you what you choose to do in life. But if there was, say, somebody came up to me and said, what did 1 plus 1 equal? I would always tell them, 1 of something else. A vector, 1, representing that vector, 1 of something else. I don't know. What are we talking about? Are we talking about hydrogen atoms? Are we talking about individual hydrogen atoms? What are we talking about? So that's my shtick on it. Hopefully it was informative. I don't really care whether you believe in it or not. I don't really, I'm not like, it's not religious for me. It's not here to convince you to believe it. It's just look at it from a different perspective. Okay. Hopefully I gave you some perspective in life to critical thinking, AI, unbreakable encryption, algorithms, and all kinds of fun stuff. And that there's an infinite amount of ways to use this, an infinite amount of fields, and maybe you learned something from it. Okay.